All right, welcome to our fourth session of ML model eval and metrics. And today we're going to talk about regression metrics. So for the first part of this, we've been hyper-focused on classification and really binary classification to kind of get a foundational understanding of how these metrics work and how evaluation works. Today we're going to step back to regression. So we'll level set on what regression is with intro to regression. Then we're going to talk about all the squared error and all the error difference calculations. Not all of them, but a small subset of them, at least 3 of them, so you can start to wrap your head around that, and then you can extrapolate that to all the other different variations and manipulations of the error derivations. So there's mean absolute error, mean squared error, root mean squared error. Those are the ones we're going to talk about and practice today. And then we're going to try to implement those in a breakout exercise. Then we're going to talk about R squared and adjusted R squared. We're going to talk about residuals, R squared, residual squared, what that is, and the adjusted R squared, how those differ from these. In terms of what we use them for and how they're calculated, the calculations for them. And then we'll touch on at the end prediction error plots. Again, kind of our third topic is usually one that we're not diving into super deep, but we're touching on good to know. So this is how you would make plots or visuals of these errors in a similar way that we make a confusion matrix for binary classification problems to really understand when and where is our model performing wrong or incorrectly. In regression metrics, in regression models, we usually do prediction error plots, plotting the predicted Y versus the actual Y. All right, let's dive in. Give me one moment while I adjust my screens here. Okay, session 4. Again, this is what we're going to talk about here. So evaluation metrics for regression. We've spent quite a bit of time talking about classification problems, metrics for classification problems, and specifically binary classification. So I want to take a minute to get your mind to shift back to regression. We haven't touched on that yet in this class session, but you'll remember it from the previous session, from the previous class. In machine learning, regression refers to a supervised learning algorithm, so we're in that domain of supervised learning, and we're using it to predict continuous values based on input features. So this is different from classification, because in classification, the goal is to predict a categorical label. 1, 0, is a banana, isn't a banana, can you identify a cat or not, predict what type of soda pop this is. But in regression, we're aiming to predict a continuous numerical value. So we're aiming to predict what is the price of this house. That's the context that we've talked about this in the past. Is it $100,000? Is it $101,000? Is it $102,000? It can really take any value on that continuum. So it's a continuous numerical value. There are a lot more kind of options for what the prediction could be in regression. There's a lot of different applications, so tried to just put these up here to get some creative ideas in your mind, but forecasting sales, revenues, profits, losses for financial planning and economics. We talked about housing prices could be based on these factors, such as location, size, amenities. Those could be your input features. Forecasting the demand for goods or services, estimating the effectiveness of marketing campaigns. So you're trying to send letters to people to try to get them to buy your product. How many people responded to that? Forecasting market demand for new products or services. How many people are likely to purchase your product next month? How many people are likely to purchase your product the following month? predicting patient outcomes, forecasting healthcare resource utilization, a lot of the similar problems to binary classification, but the difference is just going to be numerical values. So if we're looking at blood pressure, for example, that's not a binary feature anymore. That's really a numerical value that can take on a continuous range. Last thing I'll say here about regression, I know you guys are all familiar with it. Again, just trying to get your head back in that space. Here's some examples of different modeling techniques that specifically that we've talked about in the previous class, and that's linear regression. We spent a lot of time talking about linear models and their relationship between the input feature and that target variable. So this is that initial y equals mx plus b, or that y equals beta sub naught plus beta sub 1 times x plus beta sub 2 times x plus beta sub 3 times x, all up to beta sub n times n. That's the linear regression formula. That is an example of a model that would be applicable to the regression space. You could also use decision trees or random forests, but they have to be they have to be regression decision trees or regression random forests. So there you can use a decision tree model the same way that we've talked about it kind of in the binary classification sense, but the algorithm implemented for that would be a regression tree. All right, let's talk about the first evaluation metric that we're going to discuss today for regression problems, and that is mean absolute error. And in the field of data science, I'm sure many other fields as well, people really enjoy abbreviating things. So you will just see this as MAE. The mean absolute error, it's a metric used to evaluate the performance of a model by measuring the average magnitude of the errors. That's what we're looking for. What is the average size of the errors between the predicted values and the actual values? It's really simple. It's really intuitive. And it's a measure of how well the model's predictions align with these true values. So it's used quite a bit because it's just simple, intuitive to understand. Here's the formula. So MAE, the mean absolute error, is 1 over n times the sum from I to n, where I starts at 1, of the absolute value of y at I minus y hat at I. Okay, that's kind of a lot. Maybe, let me see if do I break this down on the next slide? No, I don't. So I might pull out the whiteboard so we just take a second to break this down. Because there's a lot going on here. That's a good foundation because this is all we're going to do today, is talk about these. Let me change my view. Okay. Close enough. So we have our formula here. MAE is equal to 1 over n times the summation from 1, I equals 1, all the way up to n of of the absolute value of y at I minus y hat at I. Okay, so I'll talk about this verbally and then let's go through an example and actually break it down. Remember that summation means calculate this for each of the observations in my data set. Calculate whatever's here for each of the observations in my data set. Add those all together. Divide by the number of observations. So remember that this is basically the average. That's what we're doing. So we're saying do this for each observation in my data set. So do whatever it says in this function. And then we're saying add all that together. And then we're saying divide by the number of observations. You can think of these two things together. This is just taking the average. Add it all together, divide by n. So mean squared error, so now let's break down this part. Let's break down. So now that we know that this is just the average, add it all together, divide by n. That's all that is. Let's think about this part here, what this means. So let's pull that out. So absolute value of y at I minus y hat at I. Remember that y at I is what, I just want to make sure I say this right, is our actual value, is ground truth, real value, actual truth, real, maybe test, our test data set. You know, if we have X test, we have like Y test, it could be Y test. Maybe I'll move that over so it's. Remember that Y hat is what we predicted. This is our prediction. If I predicted the house was $70,000. Oh, sorry, I put that in the wrong spot. Sorry. There we are. If I predicted the house was $70,000, but the house was actually $100,000, 70,000 minus 100,000 is $30,000. So I did that backwards. 100,000 minus 30,000 is 70,000 is $30,000. Okay. Well, what if I predicted the house was $100,000, but it was actually $70,000? Well, that's negative 30. And a prediction that is off by $30,000 is just as bad, $30,000 positive, we underpredicted by $30,000, is just as bad or just as erroneous as a prediction that is underpredicted by $30,000. So when we try to calculate these metrics, it's hard when this is 30,000, this is negative 30,000, to make a metric that properly weights those and penalizes those the same. That's why we need the absolute value. So we take the absolute value of $30,000, which is just $30,000. We take the absolute value of negative $30,000, which is just $30,000. What the absolute value function does is it'll remove that negative sign. So it just wants to know what's the true difference. What's the true difference between 70 and 100, regardless of whether it's positive or negative? Maybe I'll take a picture of this so I can drop it somewhere for you guys later, because I'm going to erase some of this. Okay. All right, so we see that. Let me erase some of this. And in green, we're going to put up here, we're going to say Y true, and this is our Y red, okay, just so we remember. So we come back to this, and we can read this now, knowing, since we just talked about what's inside here, and we can see that this is the difference between our absolute difference between our true prediction, or true value, the absolute difference between our true value our prediction and the average of that across all of our predictions. So the average, absolute difference between our true prediction, our true value and our prediction. Sorry, I keep saying our true prediction. Our true value and our prediction. Mean absolute error. This is the error. Y at I minus Y at I hat. That's the error. Absolute, our absolute value signs. Mean, this average. So mean, absolute error. Okay, let's think about just a really simple example so we can get this working. 1, 2, 3, 4, 5, 6. And this is our Y pred, or I'm sorry, Y true. Doesn't really matter, but Y true. And this is our Y pred. If we wanted to calculate the absolute error for each of these, it would be 1 minus 4, or 4 minus 1. It really doesn't matter because we're taking the absolute value. And so that would be 3 for this one. So I'm going to call this our error. It's equal to 3 for this one. 5 minus 2. It is equal to 3 for this one. 6 minus 3 is actually 3 for this one as well. And so what we would do is we would take all these errors. Our MAE is equal to the sum of our errors divided by N. 3. 9 over 3 is 3, which makes sense because we had 3 for everything. So our average error is 3 because it was 3 for everything. So we can start to play around with this if we want. We can change one of these to 1. Just forget about the 1 and 4 there for a second. Just pretend the error was 1 plus 3 plus 3. So now instead of 9, we have 7 over 3. So you can see how your error is going to change. Now our error is going to be reduced, right? Our error is going to be lower. We're gonna have it's not 3 anymore. I don't know, what's 7/3? 2 point something, right? 2.1/3, 2.3, right? Something like that. I'm not sure exactly, but somewhere in there. So you can see that our error went from 3 to 2.3. And so you can start to understand that might make sense because one of these is 1, the other 2 are 3, if it's an average of these errors. Now what if we changed one of these to 10? Maybe I should make this multiples of 3 since we're dividing by 3. What if I change this to 9? Okay, it's a little easier. We're gonna get an even number here. So now this is 9 plus 3 plus 3, 15 divided by 3, which is 5. There we go. I can manipulate these to make them straightforward math. There we go. Our error went up. Even though we have 2 that are 3, the one time we did really bad, it counted a lot against us because it's averaging across these numbers. So this is really just your plain traditional average. You can think of this as accuracy. This is basically accuracy for these types for regression types of model. This is kind of the equivalent of accuracy. How often are we on average right or wrong, off or correct from our target? And
so you're saying the 5 is you're 5 off.
Yeah,
Average.
On average, you are $5 away from having the right house price prediction. On average. So this is kind of the equivalent of accuracy. It's a really simple metric. We're not weighting anything here. We're not saying like we did with log loss. We were saying, hey, if you were really wrong, we're penalizing you more. We're not doing that here. We're equally weighting the correctness or incorrectness of the model across all of the predictions. Okay, I think that was good.
Thank you. That was very helpful.
We might do a lot of whiteboarding today. All similar stuff here. Okay, let's jump back in. Mean absolute error interpretation. It represents the average magnitude of the errors of the predictions made by the model. A lower mean squared error is better accuracy. It's a better performance. And it means that the model's predictions are a lot closer to the true values. You're approaching the true values. A higher mean squared error is a worse performance. And I realized I didn't put this in here. Maybe I should have, because we were just talking a lot about binary classification models, but this does not range from 0 to 1. We just talked about an example where it was 5. There is no limiting to the range of this to 0 to 1 like we do for other models. So you could have an error of 7,000, an error of 20,000.
So when you're talking about the lower MAE, when we're talking about like 1 being lower than 5, but like point something would like it's still that's where you're trying to get to. It's like points, 0.01. Like is that considered low, like lower in the sake of accuracy? I'm not explaining it right. I'm asking. I know you're saying that.
Is that better?
Yeah, like having it in like in that like in decimals, I guess, or not decimal. Like 0.11 is obviously less than 1. So like you're trying to get to true 0 to make well you're not trying to get to, but if your average is close to 0, then it's better accuracy.
That's correct.
Okay,
If
so
you're the
make
closer
sure-
to 0, the
Yeah.
better accuracy. But this is not broken into deciles.
Yeah, okay.
Yeah, so you won't have the 0.1, 0.2, 0.3. Instead, you'll have like 5, 30, 1,000.
Okay, so here's my question and a follow-up on that. If my number of accuracy is at 1, does that suffice for me to say, I'm okay with the 1 being the average? Or is that something that you need to know ahead of time and say, if my MAE is 5 and I didn't expect that, like, what does that, I guess, what does that tell me? Do I need to go look back?
That's a good point.
Or?
This isn't going to be as comparable across models as a metric as like accuracy, right? So accuracy, everybody kind of intuitively understands it, and you can say, hey, I have 60% accuracy, I have 70% accuracy, and then in someone's head, they can kind of grasp that and understand. The mean squared error is really dependent on your problem. So if you say, I have a mean squared error of 20,000, what does that mean? What are you trying to predict? Are you trying to predict house prices? Maybe that's not too bad. Maybe that's kind of close. It's not great. Are you trying to predict like distance driven by a car? That's probably really bad. You're probably very off. So it's a little dependent on your problem, and it's not as easy to compare. Like if you have a mean squared error of 20,000 and I have a mean squared error of 5, it doesn't mean my model's better than yours if they're different problems.
Right. That makes
Yeah.
sense. Okay.
Yeah,
Thank you.
because mine could be terrible. Depends on what you're trying to predict. So this one's a little more specific to the problem than the other metrics that we've looked at. It's a straightforward measure. It's an average of the errors, and it's useful metric for assessing the accuracy and comparing across different models. And when I say different models, not to confuse with what we just talked about, I just mean different models for the same problem. So you train a random forest and a gradient boosted tree, and you train a neural net. You want to select between those 3 models for your same problem. So it's robust to outliers in the data since it considers the absolute differences between the predicted and actual variables. And like I said, it treats everything everything equally, regardless of their direction. So like I said, the sign doesn't matter. If you make if you underpredict versus overpredict, if you make your prediction too high versus too low, those are treated the same. Those don't have different weighting in this type of metric. Scalability, this is important. Mean squared error is on the same scale as the target variable. Not everything that we look at will be, and not all regression metrics are. So it's important to know how to interpret your variable or your metric. And I'm getting all my words mixed up today. Important to understand how to interpret your metric. So when we say we have a mean squared error of 20,000 and we're trying to predict house prices, we really can say that on average, we are $20,000 off on predicting the house price. Sometimes we're off by more, sometimes we're off by less. But on average, if we add everything up, divide by n, our average difference of errors when predicting house prices is 20,000. So it's at the same scale as our target variable, where our target variable is house prices. We have all these house prices. So we'll look at one that's not at the same scale, so I think that'll make sense to you. Here you go. We're going to try it out. Here's a data set here, a very small data set. We have actual values, we have predicted values, and what I want you guys to do is just try to calculate the mean absolute error. Spend just like a couple minutes on this. I'll be back in just a second. All right, you guys able to calculate mean absolute error? Awesome. Maybe I should have gone to the slide next. Sorry to tell you the steps. I forgot I had this in here, honestly. To compute mean absolute error, first you're going to compute the absolute differences between each predicted value and its corresponding actual value. So calculate the difference, take the absolute of that, and then take the average of all those. All right, here's what we have. So absolute differences, 20 minus 18 is 2, 30 minus 28 is 2. You'll notice a pattern here. 40 minus 42 is 2, 50 minus 48 is 2, and 60 minus 62 is 2. I should have asked before I went to this slide what the answer was.
It's wrong.
Oh, did I do this
You
right?
have 25 in the end.
So.
There we go.
I thought and I was so confused because I was like, that math does not math.
1, 2, 3,
Isn't
4,
that big?
5.
Yeah.
Just 2.
2, 2, 2, 2.
Yeah, put 10.
I fat fingered it.
It happens with best.
Equals, I meant to put 10 over 5. There we go. Apologize for that. I still had the right one in the end.
Yeah.
There we go. Does that look better?
Yeah, I thought I was missing this stuff, but yes, nothing.
So sorry about that, guys. Thank you. So the mean squared error for the example is 2, and that means on average, the value deviates 2 units, which makes sense because we had 2 for everything. Again, we'll start with simple examples and then extrapolate. Okay, mean squared error, MSE. You'll notice a pattern with these namings. There, the mean and then some type of error. So the mean squared error, otherwise referred to as the MSE, it measures the average squared difference between the predicted value and the true values. So those are the steps to compute MSE. You compute the squared differences between each predicted value and its corresponding value, and then we take the average of the squared distances. All right, let's back to the whiteboard here. Let's get this one up here. We have our mean squared error, which equals 1 over n. Same summation function from 1 to n. And then we're going to do the squared differences. So instead of absolute value, we're still y at I minus y hat at I. Making sure I'm not messing anything up. Yep, okay. Squared. So instead of taking the absolute value, we're going to square it. Same thing as we have in mean absolute error. This is just the average. So take the average, add everything up, divide by n, take the average of whatever's here. And what we have here is the squared differences. So let's look at that. So we have y at I minus y hat at I squared. Let's use our other example here where we had 1, 2, 3, 4, 5, 6. We have y actual equals 1, 2, 3, and y pred equals 4, 5, 6. Oh yeah, we're gonna be off by 3 every time on this one again. I forgot. I'm gonna change it so I'm not just giving you everything that's the same number. Let's do 2, 6, 7. Okay, hopefully that's not gonna. Let's figure out our errors here. Our errors are 1 minus 2 is 1, and sorry, I got distracted. 2 minus 6 is 4, and 3 minus 7 is 4. Now, we should actually, we're actually doing y at I, so our actual minus our pred. So 1 minus 2 is actually negative 1. 2 minus 6 is actually negative 4. And 3 minus 7 is actually negative 4. But we're going to square these. If you guys remember, a negative squared, if we have negative squared, that's a positive, because that would be negative 1 times negative 1. Which is equal to 1. So a negative squared is always a positive. So just like mean absolute error, the signs don't matter. You can get rid of those. It doesn't really matter whether it's this one minus this one minus, you can swap these. It won't change that at all. You can put y hat first. It doesn't matter. That's why I always have to look, because in my head it doesn't really matter. So what we're gonna do, now we have our errors, we're gonna add them all up and divide. So 1 plus 4 plus 4 all over 3, because we have 3 things that we're measuring. N is equal to 3, 1, 2, 3 things. So that's 8, 9 divided by 3. Hey, I got a good even number here. It's 3. So our average,
You not square root it?
I forgot to do that. I was second guessing myself as well, because I was like, why is that in the same metric? So sorry. You are supposed to square each of these. Squared. So to your point, 1 times 1 squared is 1. 4 squared is 16. So 16 plus 16 plus 1. 33? Yeah. 33 divided by 3. 11. There we go. Sorry about that. Forgot to square those. That's mean squared error. So notice, I'm glad you caught me there, because I was scrunching my face because I was confused, because what I wanted to say when we got to the end of this was, notice this is not in the same scale as the variable that we're measuring here. It's hard to tell here because 11 is kind of close to 7 or something. But if I put house prices up here, if I put 20,000 and made us off by a couple thousand, you would see that this metric, because we square this here, it doesn't end up, it ends up in the squared scale. So it ends up being the squared number of whatever you're trying to measure. So it's going to be much higher. It's not, you cannot say, with mean squared error, you cannot say, my house price was off by $11. That's not the right way to use that, because we are squaring the error. Instead of taking if you did the absolute value, it's in the same scale. But if you square it, now it's twice that error. So that's not actually the right way to use that. So that's mean squared error. Okay. Maybe I'll make sure.
So when you talk about stakeholder,
Uh-huh.
and you say 11, right? That's the answer. Then they're gonna say Lynn's turn. Give me what that means. Like, tell me what that means. How would you provide a answer that, when we're looking at, let's say, the property, or what was it exactly?
House prices.
Yeah. You would say it's 11 off, I don't know if you said that off, but the 11.
I actually don't use mean squared error for that exact reason. I don't know that I should maybe recommend that. I don't know. Maybe there's problems where it makes a lot of sense. I don't use mean squared error because it's not interpretable to what the actual difference is. And there's other metrics that are pretty much close enough that measure exactly the same way this does, but have a slightly different component added to it, which we're going to talk about in a minute, which is called root mean squared error. So what if we took this square and then we took the square root afterwards to bring it back down to that value? So I prefer to use root mean squared error. We're talking about mean squared error, so then when I put a root sign here, it makes sense. But that's just my preference. I'm sure there are people that use mean squared error.
I was gonna say, so I guess when would that kind of make a little bit more sense to use this over the other one? I guess in the real world, I don't know.
Over root mean squared error?
Yeah. Because I see why the other one would make sense, because it would bring
Sometimes
a realistic number.
It might depend on what your model is trying to minimize. I don't know. I'd have to go look, but I'm going to make an assumption here. There may be some models that are trying to minimize this. So you might actually want to know what is the objective function my model is trying to minimize, and use it for that reason. But I wouldn't necessarily use it to communicate to stakeholders. I'd probably put it back in that root metric. Otherwise, they're going to be really freaked out.
Yeah.
Be like, your model's way off. So I would use the root mean squared error. Which
crashing.
Well, yeah, exactly. Which we'll talk about here next. Let's more about mean squared error. Okay, so mean squared error interpretation, how would you read the value? Really similar to mean absolute error. A lower mean squared error indicates a better model performance. It signifies, again, the predicted values are closer to the true values on average. A higher mean squared error indicates greater discrepancies between those predicted and true values. And the units of mean squared error, that's what we just talked about, are the squared units of the target variable. So they're not the actual units. So if it was in dollars, they're dollars squared. So if you house prices, instead of being off by $10,000, it'd be $10,000 squared. So the trade-offs, squaring the differences, emphasizes larger errors more than smaller ones. It makes mean squared error more sensitive to outliers. So if you're trying to compare mean squared error, mean absolute error, if you want one that's more sensitive to outliers, that's mean squared error. If think about if your house price is off, remember in absolute error, we said it's a true average. It treats all of the averages the same. Well, if you square $10,000 versus $5,000, you're gonna have a much bigger number for $10,000 than $5,000 due to that squared nature. So you're gonna have a bigger penalty for times when you're off by larger amounts. So it's more sensitive to those outliers. However, this property can make mean squared error also more robust to errors, typo there, sorry, that cancel each other out when using absolute difference. So there could be a situation where you're subtracting two things from each other and they cancel each other out. So let's talk about the mean squared. Let's calculate, I think it's even our same data set, if I'm not mistaken. Did I use the same? I think I tried to be 20, 30, 40, 50, 60, 18, 28, 42, 48, 62. Mm-hmm. Yep, okay. So same data set, so you can really get to see the difference. Calculate the mean squared error. Oh, forgot to put the steps there. Got the steps this time. What did you guys get?
20.
20?
4.
You were close. You just forgot.
Oh, I forgot that.
You forgot to average.
Yeah.
Yep.
Okay, because I was like, I'm not.
Yeah. Sorry.
You were just one step away.
Yeah.
So we're taking all of our 2s that we had in the other one. Remember, we had 2 for everything. And we're going to square that. So 2 squared is 4. And then we're going to add all those together. And we're going to divide by 5 because we have 5 examples here, which will give us 4 since we have no variation here. Okay, let's take a break. Let's take a 10-minute break here, and then we'll come back and we'll talk about root mean squared error. So come back at 7:12. All right, we are back. Root mean squared error. So root mean squared error, or the RMSE, measures the squared root of the average, the square root of the average squared differences, squares in there a lot, between the predicted and the actual values. So the steps to compute the mean squared error, these are all similar to the ones that we talked about before, but we're going to take the squared differences between each predicted value and its corresponding actual value, and then we're going to take the average of these squared differences, and then we're going to take the square root of the entire thing. So let's write this one on the board. So our last one for this set. All right, now we have the RMSE. This is getting to your question, Brenda. And the RMSE, we're going to have 1 over n, the summation from I equals 1 to n, y at I minus y hat at I squared. What does this look like? Exactly the same as mean squared error. We're going to pop a square root on here. That's it. Entire thing. And we have the root mean squared error. So we just pop a square root on and then put an r at the beginning. Root mean squared error. Okay, let's go through an example. We're going to use our example from earlier. It'll probably be different because I don't remember exactly the numbers, but y actual, we had like 1, 2, 3 or something like that. Y pred, let's do 6, 10, 2. Okay? What's our error? Our error is, and remember that I'm not going to put signs on here because it doesn't matter because we're going to square them so they would go away anyways. I'm doing some lazy math. 1 minus 6, or the difference between 1 and 6, maybe I should phrase it that way, is 5. The difference between 2 and 10 is 8. The difference between 2 and 3 is 1. And then we're going to square all these. So let's put that up here. So 5 squared, 5 times 5 is 25, plus 8 times 8 squared, 8 times 8 is 64. Second guessing myself there. 1 squared, 1 times 1 is 1. And then we're going to divide. We have 3. So it's divided by 3. I actually don't know 25 plus 64 plus, it'd be 65 plus 25. I guess that's 90. Is this 90 over 3?
Yeah.
90 over 3. I'm doing a good job today about picking numbers that end up being easy to divide by. Divided by 3 is 30. Sorry. Somebody correct me if I'm wrong. Okay, so that's 30. But we need to take, this would be, if we did it this way, it would just be mean squared error. Let's take the square root. And so I don't know the square root of 30.
5.4.
There.
I don't know how far you want to go to.
5.4, 5.5, there we go. Root mean squared error. So we take the square root at the end. It's the same as mean squared error. We just take the square root. And that 5.5, remember mean squared error, we said, hey, it's not in the same scale as our target variable. We've brought it back down to the same scale. So now with, root mean squared error, similar to mean absolute error, you can now say my house price was off by 5.5. That's appropriate now to say. So when working with stakeholders, I usually either use root mean squared error if I want to penalize heavy outliers, or mean squared error if I really want an even representation across all of the errors. I tend not to use mean squared error because it's not interpretable. I just take the square root instead. Okay, get another
Question
picture
on
of
that.
this.
Question on that. Hello?
And
Hello?
let's get rid of these.
Question on that. Hello?
She doesn't seem to hear us for some reason.
Hello? Anybody? Is there anybody out there?
Can you hear me at least?
Yeah, I can hear you.
Okay. I'll try typing a message.
Can you hear us?
So now that we've got that, let's talk just a little more about root mean squared error, RMSE. RMSE
Hello?
is a measure of the average magnitude. Oh,
We were ignored.
oh no.
That was only a minute ago.
A minute's a long time. Let's
It
see.
was less than a minute. It just started.
Can you guys hear me now?
We can hear you.
Still can't hear me?
I think someone on there end was talking.
I can't hear them. Oh, you know what? That's probably a me problem. One moment. It was a me problem. Please talk. I am so
Are you there?
sorry. Yeah, I'm here.
Okay. I had a question on that.
Yes, please.
So if we follow that last example all the way through, then it was 5.5 for the root mean. It would have been, what, 30 for the mean squared, and it would have been, what, 5, 8, 1, 14, 7 for the MAE. Okay, so why is the root squared lower than the MAE, and what does that mean?
Remind me what the numbers were that we divided by 3.
1, 2, 3, 6, 10, 2. And it was 5, 8, 1.
And we had 5, 8.
5 plus 8 plus 1.
Yeah, perfect. Okay, so that would be
14.
14 divided
By 3. Oh, I put it by 2. Sorry. So that'd be 4.66.
Okay, that makes more sense to me. That's why I asked, because I didn't know why I said it would be higher either. So
Okay.
I can tell you why it's lower though, because these differences are more extreme. So we're getting penalized a lot higher for having a difference of 8 and that difference of 5 for only 3 observations. So if we brought that down, let's do our example where everything was 3. Let's bring it down to everything having kind of an average difference here. Let's pretend these are just our errors. I don't have our numbers.
That'd be 27 divided by 3. That'd be 9. Square root of 9 would be 3.
So for this, what is our MAE?
It's going to be 3.
3. What is our MSE?
It's going to be 9.
And what is our RMSE?
3 again.
So RMSE is 3. So that one is going to be the same because there's no huge difference in outliers. And if we drop one of these down to say, it's kind of hard to do when I don't have very much data here to work with, but maybe if I change this. Okay, let's make this bigger. 3, 1, plus 3, plus 2. So we're not off very much. 1, 2, 3, 4, 5, 6. 6 of these. So what is 2 plus 3? That's 5. Plus 1 is 6. Plus 3 is 9. Plus 2 is 11. Plus 3 is 14. So 14, but now divide by 6.
It'll be 2.2 and 1/3.
2.2. Now, what if we squared each of these and then took the square root? So what's 2 squared?
9, 27, plus 8, 36, plus 1, 37.
37? And then square root?
Well, 37 divided by 6.
So divided by 6.
So it'd be 6.6 and 1/6, 6.1 and 2 or 1/8, I forget what that is. So then
Square
square
root
root of that, square root of 6 is going to be about 2.2, I think.
2.2, so 6.2 approximately. So there's not a lot of variability here. What if instead, so this is what I'm trying to demonstrate. Once I have more values here, it's easier. What if instead, actually I'm gonna leave 2 of these the same. I don't know if that was 2 or 3, it's approximately the same. I'm gonna change one of these to be really extreme. We're off by 10. Now, let's recalculate that, but we're off by 10. So 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 divided by 6 is
3.5.
3.5. Okay. Okay, now, so last calculation. So 10 squared.
Well, so you got 3 squared twice is 18 plus 8, which is 26. 1 is 27, and then 100, 127.
127 divided by 6.
12, 2, 21 and 1/6.
21 and 1/6. And then square root of 21 and 1/6.
4 point something.
4 point something. So now we can see it's higher. So before, we had them kind of like, we had some errors, we were off by a little bit, but the more extreme you are off, the more you are off, the heavier penalty you get for root mean squared error. So it penalizes greater having errors that are significantly high, that are off by larger values. Outliers, maybe you might call them, but kind of like our log loss metric penalized being very confidently wrong. You can think about this in a similar way. This is not a measure of confidence, but being greatly wrong, being very wrong, is penalized more heavily than just being kind of wrong. Is in mean absolute error, we're not taking that into consideration. We're kind of penalizing them all the same. Did that
So
help?
root mean square would be more valuable than if you're looking at like house prices or something like that.
Yes.
Because if you're overvaluing a basement, say, or something like that, then it's going to show up more in your results. Okay.
Yep. I tend to, for most of the problems, I tend to use root mean squared error more. There's probably good reasons why you might want to use mean absolute error. Maybe being off by a lot is not that big of a deal for some situations, but if you're more concerned on being off by larger numbers as opposed to smaller ones, RMSE is a better metric.
Thank you.
You're welcome. Thank you for letting me know that my sound on my computer was on mute. All right. Excellent questions, guys. I hope you guys feel like you're really building this knowledge and kind of understanding how these things work. Let's see. Okay, so interpretation, it's a magnitude of the errors between the predicted and the actual values. And just like mean squared error, the root mean squared error has better performance if it's closer to that 0 value. All of these have that same metric, I guess, for assessing. The higher the value, the worse the performance. The lower the value, the closer to 0, the better the performance. Root mean squared error, again, important to consider that it's in the same units as the target variable. We are squaring them, but then we're taking the root afterwards. And so that brings us back down, to the same scale. Okay, so for example, if it was dollars, root mean squared error is also in dollars. So some trade-offs similar to mean squared error. Root mean squared error squares the differences between the actual and values. So it emphasizes larger errors more than smaller ones. So you're being penalized more heavily for larger errors, for times where you off more from the predicted value. Okay, same example. Calculate the root mean squared error. You can make your life easy on this one if you think about it. All right, was anybody able to calculate this? You guys have two? We have two. So you can make your life easy. Look at what you already calculated before in the last problem for the mean squared error, and then just take the square root of that. So you don't have to go through all the steps all over again. You just take the square root from the last problem. You were off.
Yeah, I don't know what I was doing.
Because I don't forget when I say something.
No, I looked at it and I knew I was off. I was like,
Here's just a summary. We already talked about all of these things. This is a takeaway for you. I just thought I'd put it all on one slide so you don't have to like tab between a bunch of different slides. But just if you're thinking about what's the difference between mean absolute error, mean squared error, root mean squared error, if you come back in 2 weeks, before the exam and you're trying to remember the difference between all these, here's a slide that you can use as a takeaway for that. So, all right, we already took our break because I'm going slow. So now we're going to jump to our breakout. So for the breakout today, if you guys could go to the student folder, sorry I didn't link that today, but you know where that location is. Sorry, trying to get there myself. And download the MAE, MSE, RMSE notebook. And in this notebook, what you're going to do is create a data set. So create an X and a Y array, list, whatever you want, whichever data type object you want, using these as actual values and these as predicted values. Similar to our example, just this is 25 instead of 20. So just it's really similar to the example we did in class. You can even change these if you want to be exactly the same to see if you get the same answers. And then make a mean squared error function. I said we were going to make 3, but let's just make one function for now, because if we have time, we'll come back at the end. Let's just make a mean absolute error function. So make a function MAE. If you want, you can make the other two. And then run these values through that function. Let's spend 15 minutes on this. 7:45, 15-ish minutes, 13 minutes. If you're trying to use a sklearn package, the mean squared, what is it? The mean squared, root mean squared error?
Yeah, the root, yeah.
If you're trying to use the root mean squared error by sklearn, by the way, sorry. If you're trying to use this, just so you know, it's new in version 1.4. It doesn't mean they didn't have it before. They move things around and rename things and make them easier to find and refactor certain metrics. So this may be one that they refactored in 1.4. So it's called root mean squared error. And if you have sklearn version 1.2, which you may have if you installed sklearn at the beginning of this course, you will probably get an install error when trying to use that, just so you know. So you'll have to upgrade your version to 1.4 if you want to use that. So for example, if you want to check your sklearn version, what you could do is you could do import sklearn, you could do print sklearn dot underscore version version underscore, and you hit enter, and it'll print. So you can see I don't have that version either. I'm at 1.3.2. So that means I would need to upgrade my version of the sklearn. To do that, if you're on a Windows, I'm sorry, but if you're on a Mac, you do pip install, and you have to call it scikit learn instead of sklearn. They renamed it, and it won't let you do sklearn anymore. I say sklearn, it's an old naming. And then do dash upgrade, and hit enter. And it should upgrade this to 1.4 for you. You might have to restart.
Is there supposed to be a space after whatever
I
learn?
did not upgrade my thing.
Do I have to put the %?
No, the percent should just be there. So you just do pip space install, but it did not.
It might just give me an error that it does not recognize it.
Interesting. I'm not.
Here's this one saying.
I'm gonna have to
Mine's.
Google it.
I might have to figure this out afterwards. I don't know why mine's not upgrading, so apologize. I'm still on 1.3.2. So anyways, does anybody want to share what they came up with or what they calculated for these exercises, for one or all of these?
I'm waiting for somebody else to see if they'll do it.
Go ahead and share with us. Excellent. Very nice. So I'll pull this up let me pull this up here. There we go. So we have calculate mean absolute error. We're setting the total sum equal to 0 and the count equal to 0. And then for the true and the predicted values in zip true pred, so we're zipping those together so we can loop over both of them. Total sum is the absolute value of the true value minus the pred, and then we're increasing the count by 1. Then at the end of this, we're just dividing by that count. So we're counting how many there are in our set, We're taking the absolute value between true and pred, and we're taking that, we're adding each of those together. That's becoming our total sum, and we're dividing by the count. Great work. Then for calculate mean squared error, we're doing a very similar thing. So similar structure here, we're dividing by count, starting count at 0, looping over true pred, zipping them together, and then dividing by count. This time we're squaring them. So we're taking true minus pred, and we're squaring that value. And then for the final one, calculate the root mean squared error. We are, oh, there you go. That's a way, yeah, there you go. So we are squaring them. So the same code up above here is down here. We're still taking that, sorry, on accident. We're still taking that, those true preds, subtracting them, and then squaring them, and we're getting the count over all of them. But then at the end, what we're doing that is we're raising that to the power of 1/2. Raising to the power of 1/2 is the same thing as taking the square root. If you guys don't remember that from math, raising to the power of 1/2 is the same thing as taking the square root. Okay, excellent. This is great. This is how I calculated this. So I used NumPy, which is a package here, and I just called numpy.mean and numpy.absolute, actual minus predicted. NumPy is a package we haven't talked a lot about here, so I apologize, but it does array operations, basically. It does matrix operations, actually, but you can think about them for arrays for this. So it takes every value in this array. For position 1, it subtracts it from position 2, 1 here. For position 2, it subtracts it from position 2 here. So it does those array-based operations. So that actual minus predicted and calling absolute on that is the same exact thing that that John was doing. That's the same thing as this. For true pred, take these and this one. It's the same as this. For true pred, zip them together. For each one, subtract them and then take the absolute value. That's the exact same operation as this. I'll do that again. And then we're going to take the mean. So we're going to take the mean of all of these values. And then I did the same thing for mean squared error, but we're squaring. And then the same thing for RMSE, but I take the np.square root on the outside for this one. You can also use sklearn too. That's fine. Awesome. Let's dive back into it. Great work, guys. We're going to talk about something a little different. So really not that different because we're still in regression metrics. But we were talking about mean squared error, mean absolute error, root mean squared error, and now we're going to talk about R squared. So R squared, also known as the coefficient of determination. Sometimes you'll hear it called that. Coefficient of determination. It's a statistical measure that represents the proportion of variance in the dependent variable that is predictable from the independent variable in a regression model. So you'll hear this referred to as the goodness of fit. How good of a fit is your model to the data? Let's look at how it's measured. So the R squared formula, it's calculated as the sum of squares over the total sum of squares, which I realize we don't know what that means. That's on the next slide. So I'm going to jump to the next slides and we'll jump back to this one. So it's 1 minus sum of squares over total sum of squares. What is the sum of squares? Sometimes abbreviated SSR. So SSR, the sum of squares, is the difference between the predicted values and the actual values. It's and the mean of the dependent. Did I say the mean of the dependent variable? I believe this is the actual, and the actual, not the mean of the dependent variable, sorry. And the dependent variable. I apologize. The next one's me. So it quantifies the variability in the dependent variable explained by the regression model. what does this formula look like? What does this remind you of?
Mean squared.
It looks just like the mean squared error. So I see if you guys can still see behind me here. Kind of, if you can see behind me, the mean squared error, or I can even jump all the way back to that on the slides. Might take a minute. There we go. Looks just like the mean squared error. So it looks like this, except we're not dividing by n. So notice that's the difference. What's the difference between mean squared error and, there we go, sum of squares? We're not dividing by n.
So does anybody ever say 1 over n times SSR?
Maybe. I don't want to say no because I don't want to say that that's, there definitely could be a metric that uses that. But if it's 1 over n times SSR, then it's just going to be the mean
Squared, yeah.
squared. Yep. So perhaps I haven't seen that. I will tell you that R squared is used a lot. So most of the time, and I'll explain why at the end, but R squared is used quite often as a metric for regression models. So this is the numerator to R squared, the numerator to the right part of the equation. So we have 1 minus, and then we have this numerator denominator fraction here. So this is the numerator to it. It's like mean squared error, but it doesn't have, we're not taking the average. And that's because we're dividing by the total sum of squares. So we're not taking the average because this is on our denominator. So instead of n, this is what's in our denominator. So sum of total is the total sum of squared differences between the actual values, and this is where I meant to say, the mean of the dependent variable. So y bar, notice this is a bar here now. It's not a hat. It's a bar. That means it's the average value, the mean of the dependent variable. So if you had a bunch of house prices, the average house price might be $50,000. It's probably not the average house price. Houses are expensive, but that would be your average. So you would take every prediction from the average, and that is your denominator. So basically, you can think of this. So let's write this out first of all. Let's jump back to the board. Let's write this out. Now we have R squared. I'm building up our knowledge domain of regression metrics here. R squared, I'm going to move it down just a little bit. I'm running into this other one. Is equal to 1 minus, and we're going to do the, sorry, I just want to get the formula right here. The sum of, from n equals 1 to n of y I minus y hat at I squared all over the sum from I equals 1 to n of y at I minus y bar. I'm squaring that. Squared. Okay, so we have a squared value here on the top, and we're dividing by a squared value here on the bottom. This is the errors over all of the data set. This is MSE, but we're not dividing by n. And then this is a little different. So let's look at each of these. Let's maybe walk through an example. Let's think about, let's just make one up again. We have 1, 2, 3, 7, 1, and 5. So this is our y true. This is our y pred. And these are our errors. 1 minus 7 is 5. 2 minus 1 is 1, or the difference between 3 and 5 is 2. So if we're calculating this, the top part, it's going to be, so let's do 1, 1 minus, so we need to square each of these. So this is going to be 5 squared, 5 times 5 is 25, 1 squared is 1, and 2 squared is 4. So that's 30, 1 minus 30. And that is in our numerator, so I'm not writing this very cleanly. And in our denominator, we're gonna have yi minus y bar. So y bar, but y bar is the average of our true values. So it's gonna be 1 plus 2 plus 3 all over 3. So 6 over 3, which is 2. So y bar is the average of our true values. So y and I minus y bar. So this is going to be, y bar is always 2. So this would be 7 minus.
Can you make that a 6? Since you've already used it.
Make this a 6?
Yeah. You just said 5 down below. And you've already used it in some calculations. So 7 minus 1 is 6.
Oh, I did. Thank you. Yep. Thank you. 2 minus 6. 2 minus 6 is 4. And then 4 squared. So this would be 4. Sorry, this is so messy. 4 squared. I didn't really think through organizing this. But now we're going to move to the next one. 2 minus 1 is 1 squared. 5 minus 2 is 3 squared. 4 squared is 16, plus 2 plus 1, plus 1. 3 squared is 9, so 16 plus 10 is 26, so 29 over 26. You guys can't see that. There you are. I don't know.
Is the 1 outside of everything? Is a 1 minus 30 over 26?
Yes. Yes. You're right. All right, let me clean this up real quick because this kind of got messy. Let me think of how to reorganize this. I don't like the way that's done. I'm just going to start at the top and work down. So we have our y true equals 1, 2, 3, y pred equals 6, 1, 5. We have our errors is equal to 5, 1, 2. And if we square those, it's 5 squared. Squared, which equals 25 plus 1 plus 4, which equals 30. Okay. I think I can start to erase some of these. Got that. Okay, and then we wanted to calculate our denominator. You know what? I'm just gonna do sum of total and I think sum of squares, SSR and SST. SSR equals 5 squared plus 1 squared plus 2 squared, which equals 25 plus 1 plus 4 is 30. Y bar, 1, 2, 3. Down for myself to remember. Okay, over 6, right, over 3. 6 over 3, which equals 2. And then SST was equal to 4 squared plus 1 squared plus squared, which equals 16 plus 1 plus 9, which equals 26. All right, sorry about that. Here is a cleaner way to look at this. We have our y true, 1, 2, 3. We have our y pred. We calculated our errors, which are the difference between our y true and our y pred. Then we calculated our SSR, taking the square of these and summing those up. That gave us 30. Then we calculate our y bar, which is our average, which is 2, and we use y bar to calculate our SST. So summing those up, getting 26. 30 is our numerator. Remember, and this is our 26 is our denominator. Make sure I said that right. Yeah, okay. So now we can say that our r squared is equal to 1 minus SSR over SST, which is equal to 1 minus 30 over 26. I don't know what that is, but something less than 1. Okay, sorry that got messy, but hopefully I didn't lose you guys there. That is r squared. I'll leave that one up there. So the interpretation, r squared will always range from 0 to 1. And a value, this is back to, finally, a metric that ranges from 0 to 1 across every model training. So a value closer to 1 represents a larger portion of variance, and the dependent variable is explained by the independent variables in the model, suggesting a better fit. Conversely, a value closer to 0 indicates the model explains very little of the variance in the dependent variable, implying a poor fit. So the limitations to r squared, it should be interpreted in caution and conjunction with other metrics, because it can be influenced by a number of predictors in the model and may not necessarily indicate quality or accuracy of these predictions. So let's work through, I think I have a breakout exercise for us. Yeah. We're going to do the same type of work that we just did for our other one. Let's spend 15 minutes working through the breakout exercise on r squared. Here's what this one looks like. So here's the r squared one. So consider this example where this is we only have one x variable and we have one y variable. create a regression model, linear regression. I think I even created the linear regression model in there. Correct me if I'm wrong. And then calculate. So let's see, there we go. I think I put it up to here in there in the notebook, I believe. So calculate the SSR, the SST, and the R squared. Try to do that exercise yourself. Try based on the formulas that we've put up here. Try to calculate SSR, SST, and R squared. Spend 15 minutes on that. So let's come back at 8:25. I realized I said I was going to say this and then I didn't. I don't think there was a good spot for me to talk about this in the slides. But to Brenda's question earlier about how if we have one model trained on one thing, one type of data set, and another model trained on another thing, another type of data set, can you really compare them with root mean squared error, sum of squares, or not sum of squares, sorry, the first three metrics, mean absolute error, mean squared error, and root mean squared error, and you can't. You know, if we're training on housing prices, it's going to be at the same level or granularity of that y variable for those metrics. R squared, on the other hand, is not at the same granularity as those other metrics. So it gives you a value between 0 and 1. So you have kind of an estimate, a thumb in the air, for understanding how much better my model is than Brenda's, even though we're using two different data sets and they're two different problems. So it's a little more similar to accuracy or precision or recall and some of the other metrics that we talked about, in the sense that you shouldn't compare those things, but you can understand what that type of performance means. It's interpretable across them. So here's a good link that I found, a good answer that I found about the relationship between R squared and MSE. And I think that's why, while you guys work, sorry, I think that's why R squared, you'll see it a lot when people put up the performance of their model. Almost everybody asks, what is your R squared value? What is your R squared value? Because they really, it's easy for them to interpret and understand, kind of thumb in the air compared to other models and other baselines, about how well that's doing comparatively. It's a good point of reference because it has that 0 to 1 scale. I don't remember if I talk about this anywhere, so let me scroll through the slides. Oh, maybe I talk about this after adjusted R squared. So let's continue the breakout session. I might be getting ahead of myself here. There's one other thing I want to say on that, so I'll say that at the end. All right. Does anybody want to share their work or what they were able to do for this?
I updated my thing last Friday, but we were doing this.
That's fine. I distracted the people in the room here, so does anybody online have something they'd like to share?
I want to post it.
Excellent.
Sorry.
Wonderful. Thanks, Ted. That right here. There we are. So we have the SSR calculated, use NumPy just like me. Here we go. Nice.
Very the shortcut. I mean, if we could use these tools, then I figured it might as well.
Yeah, it makes it a lot faster. You don't have to, it's such a shorter line here. So we call numpy.mean on the y vector here. And we take ypred minus numpy.mean at y, and then we're going to square that. And this is for the SSR. And then the SST, we take, I'm double guessing, second guessing here. SST is numpy sum of y minus numpy dot mean, the average value here at y. Is that how we talked about that today? This one,
For which one?
I'm doing this right. Average at y squared, y minus y pred. I don't think we took the. Come back to this. I'll double check, make sure this is right. But I think it is, but I will double check. So we are going to take 1 minus the SSR over the SST, and then we're going to print that out. Excellent. That is the same thing that I did here. Okay, let's talk about adjusted R squared, and then we're going to finish off with the error plots. And we should be done for today. So just 2 quick topics here. Done with breakout sessions. Adjusted R squared is a modified version of the R squared value, the coefficient of determination. You may hear a lot of people ask, what is your R squared? But a lot of people also may ask, what is your adjusted R squared? I would say this is kind of a more popular metric. It's R squared has a longer history, so you may see it in some older kind of documentation, or somebody maybe who's been in the field for a while will be used to R squared, but adjusted R squared definitely is a more robust way, and it's a preferred metric. Just like we talked about, there's mean squared and then there's root mean squared, and why root mean squared is better than a mean squared, but we talked about. And so you might use root mean squared instead. This is similar to that. So adjusted R squared. It provides a more reliable measure for the model fit for models with multiple predictors. So the adjusted R squared penalizes the addition of unnecessary features if you add more X variables that don't significantly improve the model's explanatory power. So that was a lot of words. Let's look at this calculation, and then I want to talk more about what exactly adding more features, explanatory power, what does that mean? So adjusted R squared is 1 minus R squared times n minus 1 all over n minus k minus 1. So n is the number of observations, your sample size. K is the number of predictors. So this is the big change that we're making here in this metric is we're dividing by K. So we're adding a component to this metric that considers the number of features. So in most of our examples that we've just been playing around with in class to just understand these metrics, we've had one X value, one X feature. But as you guys know from the previous class, most of our problems have lots of X features. If we're thinking about house prices, you can have the number of bedrooms, you can have the number of bedrooms, the number of the square footage of the house, how many acres is your house on. So you can have all this information about a house, all these pieces of information. Those are your X features. Those are your predictors. You can just keep adding predictors. We can just keep adding data. Not every piece of data that we add will be informative to the model's prediction. Sometimes we're going to add features that don't really add a lot of information to what the model is predicting. And that's what this variable, when we talk about goodness of fit, that's what that is measuring. How good is the fit of your features that you put into your model in terms of how are they adding value to what it's actually predicting? So if we're adding a bunch of features, if we're adding tens and 20 and thousands of features, but it's pretty much just adding noise to our model, your R-squared value is going to reflect that. Your adjusted R-squared value is going to reflect that. So the adjusted R-squared is used a little more in traditional statistics and traditional modeling, where they really want to make sure that you have only features that are informative to the model in them. I can tell you that as we move more towards, so this leans more towards like linear regression, if you're using linear regression and some of those more traditional foundational techniques. I can tell you though, as we move more towards neural networks and just huge amounts of data, think Facebook or Amazon, and we want to process a very large amount of data and put all that information into a model. We're not really picking and choosing whether one feature or another feature is adding a lot of information to the model. So R-squared is really, like I said, just focused more on, or adjusted R-squared is focused more on those traditional statistical methods. And you will see it less in practice of like regression problems using neural networks or those huge, vast amounts of data, because we're not so concerned with trimming down our features to make them like just the perfect set. Okay, that's what I wanted to say there. So the interpretation for the adjusted R-squared, again, it ranges from 0 to 1. It's similar to R-squared. A higher adjusted R-square value indicates a better fit for the regression model to the data. However, you should take into account a number, however, adjusted R-squared takes into account a number of predictors. So it penalizes models with more predictors unless they provide significant explanatory power. So if you're adding more features to your model, they have to be really doing something significant. It penalizes you for just adding features that don't do anything. So again, this is really your traditional machine learning methodology area that this is used in. It's still a relevant metric, but I wouldn't say it's necessarily relevant to all the cutting edge like vision system work and that type of stuff. Okay, so mean squared error versus adjusted R-squared. So I just put this in here again. You may have some questions. We just talked about this adjusted R-squared and this R-squared value. What's the difference between mean squared error or even root mean squared error for that? Basically, mean squared error, root mean squared error, mean absolute error, these are metrics that the model uses to optimize for. It's measuring its performance in terms of loss. How much is what it's predicting off from what the actual values are. Those are all manipulations of measuring that. When we look at R-squared, when we look at adjusted R-squared, it's looking at understanding how good is your fit to your model in considering the number of features that you put into that. It's maybe not a good fit. There could be a better fit if you reduce the features, reduce the noisy features. So it's less about the actual performance of the model. It's something that you would consider for parsimony, how parsimonious is your model when selecting your model. So mean squared error, root mean squared error, mean absolute error. These are all metrics that you would use in cross-validation and hyperparameter selection and model tuning. The R-squared, adjusted R-squared, this is something that you might put out after that process. You've selected that and you have 3 different types of models that you're trying to choose between, and you're looking at them and you want to kind of analyze the difference between them. So if we're looking at a random forest and we're looking at a regression, linear regression, and we want to know the difference between how well fit those are, what's the goodness of fit. Excuse me, that's adjusted R-squared. Okay, I said break, but we're not going to take a break because we took that earlier. I put these in different places. Moving on to prediction error plots, unless anybody has questions about R-squared, prediction error squared, adjusted R-squared. No, okay. Prediction error plots. So this, and I apologize because this is blurry, but you guys all get the idea, and we can even, I think I'm going to whiteboard something here with this. But prediction error plots, also known as residual plots, they're graphical representations to assess plot the difference between what you're predicting and what the actual values are. So on the x-axis, we have y. What were the real values of the house prices? And on the y-axis, we have y hat. What were the predicted values of the house prices? I realize I should take a minute here to talk about something which we've been using this whole time, and I've been calling them errors, but sometimes you might hear them called residuals. So a residual is also known as the prediction error. Sometimes it's referred to as E at I, and it's the difference between the y and the y hat. So it's y minus y hat. It's the deviation at each data point from the model's prediction. So when we're up here and we're calculating errors, this is E at 1. This is E at 2. This is E at 3. So we've been calculating the residuals this whole time. We've just been calling them errors. So the plot typically has a scattering of points, and we can look at these distributions, and you can identify patterns and trends and figure out, hey, there may be an issue with my model performance here. So I want to whiteboard this for a second. Let's think about that. Oh yeah, this side doesn't work very well. There's something interesting about this balance of this board. But so we can plot all of our predictions on this chart here. It's really interesting. Where we have y and y hat. And say we have let's make a data set here. Let's make our y true, and let's make a y pred. And I'm going to spread y true out just so we can kind of get all along this number line. Let's say we have, let's just do 1, 2, 3, 4, 5. Sure. Let's do 1, 2, 3, 4, 5. So this is 1, this is 2, this is 3, this is 4, and this is 5. And let's say we had a perfect model. Let's start with that. 1, 2, 3, 4, 5. So let's say when it was 1, we predicted 1. When the house was price was 2, we predicted 2. When the house price was 4, we predicted 4. And when it was 5, we predicted 5. So what would that look like? Well, y was 1 and we predicted 1. Then y was 2 and we predicted 2. Then y was 3, we predicted 3. Then y was 4, we predicted 4. Then y was 5, we predicted 5. So going down the diagonal here of a prediction error plot, sometimes these are called prediction error plots, sometimes these are called predicted versus actual. Oh. This is what a perfect model would look like. So a diagonal line along this plot. If your dots show up along this diagonal line, that's a perfect prediction. Okay, so what if we underpredicted for every single prediction? What if instead our y pred, we underpredicted, and when it was 1, we predicted 0. When it was 2, we predicted 1. When it was 3, we predicted 2. When it was 4, we predicted 3. And when it was 5, we predicted 4. We underpredicted for every single prediction. Well, if it's 0, we predict 1. If it's 1, we predict 0. When y true was 2, we predicted 1. When y true was 3, we predicted 2. Okay, so you get the idea here. So this is what underpredicting would look like. So if we're underpredicting for each prediction, we're under this curve. You can imagine we can do the same thing with overpredicting. If we did 2, 3, 4, 5, 6, it's just going to be same thing, but it's above the line. If when y true was 1, if we predicted 2, it's up here. When y true was 2, if we predicted 3, it's up here. If y true was 3, we predicted 4, it would be here. So over prediction is when you're over the line. Under prediction, you're under. Okay. So get that. Usually your model's not always I just did that as an example. Usually your model is not always correct, and it's not actually always predicting over or predicting under. Instead, what you're often going to see is some dispersion. You see some dispersion of predictions. And maybe it looks something like this. So sometimes you're going to be over predicting, other times you're going to be under predicting. But now you know how to read this plot. You know that down the middle, if there were any lines here, that's where it's exactly correct. You know this is where we're under predicting, and you know this is where we're over predicting. So these types of plots. This is the equivalent for regression problems as a confusion matrix. Just like a confusion matrix allows us to know where is our model getting it right, where is our model getting it wrong. Since regression problems don't have like an exact answer, you can be a little off from the answer, a lot off. Maybe our plot goes like this or something. You know, maybe we decide, whoa, when we get way up here, we're really off from our answer, but when we're in this area, we're doing pretty well. So it can kind of start to enable you to look at your errors, look at your residuals, and see where are things off and where are things going wrong. Okay, how are we feeling? Prediction error plots? They're pretty straightforward. Just 2 data sets, X and Y. Okay. I think that is all I have for today. So I will pause the recording here and see if you guys have any questions. Give me one moment.